In this lecture, I want to talk about inverse functions, what an inverse function is, when does one exist, and how do we find one. So let's start with kind of our general idea of what a function is, that it maps things from a set X, elements of a set X, into an element in set Y. So if I have some element X here, then F maps it to, or kind of associates it with a point Y in the set Y. So we call this the domain of the function. This is the range of the function, and this is Y, but it's also the image of X under this mapping. All right. So basically, what the inverse does is it starts with Y and takes it back to X. All right, so it's a mapping that takes things from the range of Y and maps them back to the thing that they started with. So you can think of this as undoing. That's really what, if we want to kind of have a theme for this lecture, is the inverse functions undo each other. All right, so this is the idea here. It takes something that has been mapped to Y and brings it right back to what it started with. So notice that the domain of F is X, and the range of F is Y. But then F inverse is going to start with, so this actually, Y is the domain of F inverse, and X is the range of F inverse. So kind of another way to think about this is, with the inverse, we just switch the domain and the range. We switch the X and Y. The other thing to note here is that F inverse of F of X is X, right? So in other words, at this point Y, we can also think of it as F of X. It takes F of X back to X. So let me give you a specific example. Get away from, I think the set notation or representation is one way to think of it, but we want to think of things like if we have a function 3x and another function 1/3 x, getting into like linear functions or quadratic, that sort of thing. What do we mean when two functions are inverses? All right, so here what I want you to notice is that if I take g of f of x, all right, so in other words, I'm putting f into this, I'm replacing x with f of x, all right? So what I'm really doing is I'm saying g of 3x, which is 1/3 times 3x. Well, 1/3 of 3 is 1, so that's just going to give me x. And likewise, if I take f of g of x, so that's f of 1/3 x, well, that's 3 times 1/3 x, right? I'm taking this 1/3 and I'm putting it in for x in f. 3 times 1/3 is 1. So you can see what happens here is these functions undo each other. They get us back to what we started with. And this undoing is kind of the characteristic property of inverses. In fact, we can generalize. This is just a specific example, and you can see here too, just from kind of a common sense point of view, right? If I take a number and I multiply it by 3, and then here I divide by 3, I should get back to the number I started with. Or if I take a number and divide by 3 and then multiply by 3, again, I'll get back to the number I start with. So that's what we mean by the undoing. So in fact, we have kind of a general statement. We can say that if f of g of x equals x, and g of f of x equals x, then g is the inverse of f. All right, this is basically a way to test to see if two functions are inverses of each other, and this would be kind of a way to do it. We just plug one function into the other and then switch, and we should get back x in both cases. So to finish the sentence, g is the inverse of f, and we denote the inverse of f as f inverse. Okay, so graphically, well, not just graphically, but also in terms of just the points that we're looking at, since the domain we already said, so the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So another way to think of this, I mean, we just think the domain and the range these are sets, but let's think about what this means in terms of an individual point. So if the point AB is on f, then the point BA is on f inverse. All right? Because what we're doing is we're swapping the domain and the range. And that means if we're swapping the whole sets, that means every individual point, right? A is part of the domain of f. B is an output. It's the range of f. So then, since the range of f is the domain of f inverse, then B should be in the domain of f inverse, and then likewise A should be in the range of f inverse. So let me give you, let's go back to our example where we had f of x equals 3x. All right. So clearly, if I put in 1 for x, I get 3. So this point is on the graph of f. All right. So let's take a look at g of x. Well, we called it g, but after we tested it, we actually found that it was f inverse, and we'll call that 1/3 x. Well, note now that if I put in 3 for x, I get back 1. Right? So if 1/3 is on here, 3/1 is on here. So this is a specific point. That what this is saying, though, is for every point that I could find that is on the graph of f, if I flip those 2 points, switch the x and the y, then that point will be on f inverse. So graphically, if we think about what this means graphically, so let's put in this point, or this, not this point, this line, y equals x. All right. Now, notice that this means anywhere along this line, the y and the x values are the same. So if I were to switch them, I would get the same point. So essentially what we're doing when we switch the x and the y is we are going to reflect the graph of f over this to get the graph of f inverse. So let me just use another color to demonstrate that. So for y equals 3x, let's graph that first. So we go 1, and then 1, 2, 3. So we know, well, there's your 1, 3. We also know that it goes through the origin, so that's the graph of f. So what about f inverse? Well, we know that the f inverse goes through this point, so we can come out here to 3, 1, and then this also goes through the origin, so we have something that looks like this. It's sort of straight, and that's f inverse. So notice, though, if I were to take this line and basically kind of flip it over this line, y equals x. So I take this part and flip it over, I get this, and down here, if I flip this over, I get, f inverse. So it's a reflection, is what we call it, across this line, y equals x. And functions that are inverses of each other will always have this property. Well, there'll be a reflection of each other across this line, y equals x. Okay, so the next thing I want to say a little bit about is which functions have inverse. Do all functions have inverses? Another way to say it, we could basically say that every function does have an inverse, but what we want to know is the inverse of a function itself a function? All right. So let's start with the kind of graphically the test that we used. Right. So if I had, for example, let's just draw on a random parabola here. So we used the vertical line test. Right. We would draw a vertical line, and as long as we can draw a vertical line anywhere, and it only hits the function, or only hits the graph in one point anywhere, then we know that we have a function, because that means that each x is associated with only one y. If we're to hit the graph in another point, then that same x will be associated with two y's, and we wouldn't have a function. All right. So let's put in our line y equals x. think about what we would need here in order to, so we have this vertical line test. What we'd like to do is come up with a test that would help us to know if a given function, if its inverse is itself a function. So let me just go ahead, I'm going to try to reflect this parabola. I could have drawn it a little more carefully, but let's just see if I can kind of just sketch in. So it would kind of go through here and kind of come back around. So this might be the inverse, or the graph of the inverse of this original function. All right. But what happens now if I flip my vertical line? What I end up with is a horizontal line, right? Now, first you can notice that the inverse is not a function, right? Because it's going to hit in two places. All right, but if without drawing the graph of the inverse, is there a way to determine whether or not this original function has an inverse that is a function? In this case, we know that its inverse is not a function because we've drawn it. But without drawing the inverse all the time, is there a way that we can just quickly look at a function and determine whether or not it has an inverse? You know, it's the vertical line test is nice because we can quickly determine from the graph, from a given graph, whether or not that graph is a graph of a function. But notice if I take this vertical line and I flip it over the line y equals x, let me get another color here, that what I'm going to have, if I take this and I kind of flip it over the line y equals x, I am going to end up with a horizontal line. All right? So notice that this horizontal line intersects the original graph in two places, and those two places are these two places, right? If we were to flip it over, they would be these two places on the inverse. So this is the horizontal line test. And basically what it says is, if we look at f, start off with this function f, if a horizontal line hits the original function in two places, then its inverse will not be a function. All right, and we see that right here because when we flip it over, then we have a vertical line that hits this inverse, the graph of the inverse, in two places. All right. So another way to say this is that f is 1 to 1. All right. So there is one y associated with each x. That's what we need for it to be a function, but we also only have one x associated with each y. That's what we need for the inverse to be a function as well. All right. So we actually can see right here. Let's say if I called this f of x equal to x squared, then we see. I mean, it's not exactly x squared, but it's close enough. We can see, well, the inverse is not a function, and actually the inverse is, well, maybe I'll just kind of keep it in the same color. The inverse is x equals y squared. But if we look at our parabola, it hits in two places. The question is, could we restrict the domain of our original function so that it does have an inverse? Notice that it's when this thing starts to come back up again that a horizontal line will hit it on the other side. So one way that we could potentially, and this will be important when we start talking about inverse trig functions, we can restrict the domain of the original function. So instead of having this thing come up or come down and come back up again, let's just draw half of it. Let's just draw this half. All right. So we will call this f of x equal to x squared, only for x greater than or equal to 0. We're going to restrict the domain. We're not going to allow any negative x values. Notice now it does pass the horizontal line test, right? Any horizontal line that we could draw through here is only going to hit the graph in one place. And now, again, if we go ahead and draw in the line y equals x, we can flip this thing, reflect it across, and we would get a graph that looks like this. And what do you think undoes squaring? If I square a number, how could I get that number back? Well, the inverse, as you might guess, will be the square root. And this looks like what we would expect the square root function to look like. All right, so that's one way that we can kind of take common functions and we can restrict their domains so that they actually do have an inverse. So the next and last question is, how do we find the inverse? I mean, here it wasn't too bad, but let's say we had, so I'm going to kind of separate us off here. Let's say we had this function x cubed minus 1, and I wanted to find the inverse to this function. So, certainly I could do it graphically, but and there'll be some expressions where it's not possible to do this algebraically, but in some cases we can. So f of x is the same thing as y, right? So we have y equals x cubed minus 1. But the big idea here with inverses is that we're switching the domain and the range. We're just switching the x and y. So we're going to do that here. So I'll switch the x and the y, and then I'm going to solve for y. So the first thing is I'll subtract 1 from both sides. So now I have that x minus 1 equals y cubed, and then I'm going to take the cube root. All right, so the cube root of y cubed, well, that's just y, so y equal to the cube root of x minus 1. So this would be, well, we should verify it, but we suspect this will be our inverse. Let's go ahead and try. Let's call this g of x because we don't know if it's f inverse yet. Well, we kind of do, but let's pretend we don't. So f of g of x is f of, well, g is the cube root of x minus 1. So I'm going to take this and put it in here for x. So that's going to give me the cube root of x minus 1 cubed minus 1. Well, the cube root and the cube kind of undo each other, and I'm left with x minus 1. Oops, this was supposed to be, oh, this is that right? Let's see. Sorry. Okay, so this I should have added. How did I end up with, so that I switched this. That should have been minus. There's a plus, 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 plus. So this should be plus. If I really did start off with a minus, right, then that should have stayed minus, and then I need to add 1 both sides. Sorry about that. So this should be plus 1. Here's plus 1. So I have a plus 1, minus 1. So that gives me x, and that's what I want. I want f of g of x to give me x. You probably caught this mistake long ago, but anyways, it's fixed now. Let's try g of f of x. So now I'm putting f of x into g, right? So in other words, I want to take this x cubed minus 1 and put it in here for x. So I have the cube root of x cubed minus 1, cube root, so that's going to have a 3 on it, x cubed minus 1 plus 1. Well, I can drop those parentheses, and the minus 1 and the plus 1 just give me x cubed, and I'm taking the cube root of x cubed, so that just gives me x. So this is indeed, now that I have it correct, I have a plus 1, because again, if we're thinking about them undoing each other, this is a minus 1, the plus 1 undoes the minus 1. All right, so in general, we would just switch the x and the y and then solve for y, and then you could check to see whether or not what you found is indeed the inverse of the original function.